start. La la la. All right. Hem. 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 I will begin. Dearly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So my class seems to be larger today. Some of you don't belong here. Are you visiting? Show of hands, who's CFA in the back, right? So, are you guys taking calculus in high school? Or so you're curious what this is? If you're really curious, you can look on YouTube. I have many of these posted, so you can see how I abuse the students. This will be a relatively short lecture today, 4849. If that doesn't make sense to you because you're a visitor, there's a good reason. It doesn't make sense. So we're talking about series. All right, so numerical series. In particular, we're trying to give a meaning to the sum k equals 0 to infinity of a sub k, which we could write in long form as follows, right? This is a0 plus a1 plus a2 plus ... I mean, without end, right? And so the question is, how did we actually define that carefully? Remember last time we said, well, this is equal to the limit as n goes to infinity of the sum k equals 0 to n of a sub k. And I gave a name to the thing inside the parentheses. What was that called? The series of partial sums. Your heart's in the right place, but that was the wrong term. I mean, this be called Sn, right? So Sn is the nth partial sum, right? It forms a sequence of partial sums. So, like, what's the sequence of partial sums look like? Why is it a sequence of partial sums? Well, if we were to list them, what does it look like? Of course, on the one hand, it's S1, S2, S3, and so forth, but what are those actually? Like the first partial sum is a sub 0. The second partial sum is a sub 0 plus a sub 1 in our current setup. The third partial sum is a0 plus a1 plus a2, and so forth, right? So the question of whether or not a series converges depends on the convergence or divergence of this sequence of partial sums. Last time, we worked out the nth term test. What did the nth term test say? Recap. We learned that if the limit as n goes to infinity of a sub n is not equal to 0, then the sum, let's see here, sum k equals 0 to infinity of a sub k diverges. So this is the so-called nth term test. If you don't like, by the way, something you should know, it doesn't matter if we do this with k or if we do this with n. Either way, it's the same thing, right? That's just a different notation for the same series, right? Okay, so next up, I wanted to prove for you guys. Well, so here's the thing. The question that you guys were asking me after class, and it's a good question to ask, is that if the limit as n goes to infinity of a sub n is equal to 0, then does the series k equals 0 to, no, I'm going to use k here instead of n. if the limit as k goes to infinity of a sub k is equal to 0, then does the limit from k equal to 0 to infinity of a sub k converge? All right? So that's one of the central questions of this part of the course, right? And thinking that this is true is, I would say, it's one of the fundamental confusions of this course. It's just not true. So, although the thing is, at the moment, we don't quite have the technology to give you a good example. I'm just going to tell you, flash forward, and this is probably something we'll do Monday, all right? You can prove that the sum k equals 1 to infinity of 1 over k, all right, which is 1 plus a half plus a third plus dot, 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 dot. Right? This is an example of a series with the kth term going to 0, right? And yet, this series diverges. This is a divergent series. So, in fact, the answer to the question is a definitive no. But I'm not going to be able to prove that for you today. I just wanted to answer the question today to try to start driving this home to you. All right. So let's go back to what we can say at the moment in our current stage of development, which is properties of convergent series. So here's the deal. If the sum from k equals 0 to infinity of a sub k is equal to big A, and the sum k equals 0 to infinity of b sub k is equal to big B, all right, where a and b are real numbers, and if c is a real number, then we have a few things we can say. All right? So like number 1, the sum k equals 0 to infinity of a sub k plus b sub k, some parentheses here, is equal to the sum k equals 0 to infinity of a sub k plus the sum k equals 0 to infinity of b sub k. By the way, it kind of wears you out writing k equals 0 to infinity on these kinds of propositions. If it's the same k equals 0 to infinity all throughout, and if it's not a detail of the calculation, you can leave off the infinity and the k equals 0 at the bottom. But don't do that in an argument where those details matter. Yeah? So what I'm trying to say is, like, item 2, I could write more briefly like this. The sum of c a sub k is equal to c times the sum a sub k. That would mean that I'm just omitting what? What am I omitting? What's understood here? Now, you're like, hey, you certainly don't endorse this philosophy over integrals. I remember you took points off last test when I flipped from definite to indefinite. That is true. I'm hypocritical. What can I tell you? But I don't know. There's no really danger for confusion here because there's not definite versus indefinite series. There's just series, right? Okay, so how do we prove these? So consider the nth partial sum of the sum k equals 0 to infinity of c a sub k plus b sub k, right? Let's look at that, and let's call that thing Sn. So this would be the sum k equals 0 to n of cak plus bk. Let me just write those out. That's ca1 plus b1, parentheses, plus ca2 plus b2, parentheses, plus dot, 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 dot. Eventually, we get to CAN plus BN. Right? That's just a finite sum of terms, right? How can we can do algebra with that, right? I can factor C out and group all the A terms, right? I can put all the B terms together. What's that give me? C times A1 plus A2 plus da 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 plus AN plus parentheses B1 plus B2 plus da 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 plus BN. Right? And so what we're looking at here is C times the sum K equals, oh, I'm supposed to have a 0 on that first term. What happened here, guys? Don't let me get away with that. What did I forget to, let me squeeze it in. Well, let me just do some erasing. Sorry, guys. That was supposed to go 0, 1, right? 0, 0, 1, 1. My apologies. Of course, when you CFA guys are not here, I don't make mistakes like that. All right. No, I am human. It's true. Okay, anyway, so k equals 0 to n of a sub k, yeah, plus the sum k equals 0 to n of b sub k. So this is really nice, because what it says is that the nth partial sum of this new series, CAK plus BK, is connected to the nth partial sums of the given series, A sub k and B sub k, right? In particular, thus, calculate the limit as n goes to infinity of Sn is equal to C times the limit as n goes to infinity of the sum of k equals 0 to n of a sub k plus the limit of, now this thing I'm doing right now, why can I do it? What law of sequences am I using? How do I know that I can break the sum of this sum up and pull the constant out of the sequential limit? Well, we proved that the other day, right? We proved that the limit for sequences has this linearity property, right? So and what do I know about it here? I know that these these are defined to be what? This is given to be A, and this is given to be B, right? Because these series converge to A and B respectively, and that's the limit of the sequence of partial sums through the A series, and that's the limit of the sequence of partial sums through the B series. And so there you have it. This limit proves exactly, well, it doesn't prove 1 and 2. What does this prove? Therefore, the sum k equals 0 to infinity of CAK plus BK is equal to C times the sum k equals 0 to infinity of a sub k plus the sum k equals 0 to infinity of b sub k. And then so you guys tell me, how can I get 1? Set C equal to what? Set B sub k equals to what? How do I get 1 from what I proved? C is equal to 1, yeah. And for the other one? Yeah, B sub k equal to 0 for k equals to 0, 1, 2, and so forth. Okay? So there you go. Now, if we have two convergent series, we can build new convergent series by either multiplying by a number or adding them together term by term, right? And they're similar. Through this essentially the same calculation, you could tell me there's a corollary to the proof here, which would be what? What's a corollary? a related result, right? If the sum of a sub k diverges, then the sum of CAK diverges as well. So if I have a divergent series and I multiply by a number, guess what? Still divergent. All right. So let's, oh no, sadness. Uh-oh. Oh man. Didn't bring my, you know, uh-oh, got no choices. I can either use this smudgy eraser or my hand, which is worse, I don't know. There we go. So, next up, we talk about the so-called geometric series, all right? So let me tell you what this is. If we have A plus AR plus AR squared plus ... which, so that could be written the sum k equals 0 to infinity of what? A r to the k. So this is, by definition, if there exists an A and an R such that this happens, it's said to be a geometric series, all right? So this is one of those very nice special cases where we can actually calculate the nth partial sum. Let me show you how. All right, so first of all, what is Sn? A plus AR plus AR squared plus ... plus AR to the n by my definition. All right? And then the neat thing here is if you take that and you also multiply that by r, right, you get AR plus AR squared plus AR cubed plus AR to the n plus AR to the n plus 1. So I took the liberty of writing one more term out in the top, in the one above, okay? So you look at that, you go, wait a second. This gives me a way to get a formula for Sn. What can I do? How can I find a formula for Sn from what I've written on the board? We had such fun with the telescoping series last time, right? So we could do something kind of similar here, right? I mean, we could look for some sort of systematic cancellation, right? Don't tell the other math professors I did this. All right. So what you got is Sn minus Rsn equals to what? There's a systematic cancellation. See it? Use your imagination. Yeah, so what do we got? We got A minus A r to the n plus 1. Therefore what? So we got 1 minus r times Sn is equal to A minus AR to the n plus 1. And
where did the AR to the n minus 1 go? Does it cancel out somewhere?
there's an AR to the n minus 1 in here.
Oh, there is?
You gotta use your imagination. Yeah. But imagination aside, by algebra, we get Sn is equal to A minus AR to the n plus 1 divided by 1 minus r. So therefore, the sum, k equals 0 to infinity of AR to the k, is the limit, as n goes to infinity, of the nth partial sum, which we just straight calculated is a over 1 minus r minus a r to the n plus 1 over 1 minus r. Now, the reason I broke up that expression into two pieces is what? I mean, this is case-wise, right? So this is equal to a over 1 minus r if what? The absolute value of r is less than 1, right? And it's equal to what? It's equal to infinity if the absolute value of r is greater than 1. And by the way, r is not equal to 1 in this calculation, right? In fact, r was not equal to 1 once I went from here to here, right? We can't divide by 1 minus r if r is equal to 1. But hey, if r is equal to 1, we already proved that that one diverges last class. That was my first example, right? 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 diverged. And this would just be a constant times 1 plus 1 plus 1 plus 1 plus 1, which diverges. So we already know that case diverges. In fact, I can, not following from this equality, but I can throw equals into here, logically speaking, right? By this corollary and what we did last time. And there you go. This is the geometric series result. If we have a series which is geometric, it either converges to a over 1 minus r, or what? Or it diverges. So example, if we have 0.9999999, okay, it's enough. That is equal to what? 9/10, right? Plus 9 100ths, plus 9 1,000ths, plus 9 10,000ths. So what's going on here? So you can identify, this is geometric. Here a is equal to 9/10. And if we look at a sub k plus 1 divided by a sub k, we get what? So here, a sub k is what? ar to the k, right? So what is my a sub k here? It's, oh, let me not say that. You just tell me. I'm making it too complicated. What's r? How do I get from one to the next? What's the ratio I have to multiply by here? Yeah. 1/10. Yeah. Now, how did you find that? I mean, you can find that by taking any two successive terms in the series, right, and dividing one by the other. If the series has this property that whenever you take any two successive terms, you know, one after the other, and you divide the next one by the last one, if you always get the same constant, that means it's geometric, right? So like a test for whether or not a series is geometric is what? If you can get a sub k plus 1 over a sub k equal to some number r for all k, if that's the case, then it's geometric. If it's not the case, then it's not geometric. Geometric means every successive term in the series you're adding up is always related by what? The same multiple. Yeah. Okay, anyway, so is r less than 1? It is. So this converges to what? a over 1 minus r, which here is equal to 9/10 over 1 minus 9/10, otherwise known as 9/10 over 9/10, which is equal to 1. So here you go. We can prove that 0.999 repeating is equal to 1. Now, you've been told this as school children, right? But to carefully prove this, this actually requires an understanding of sequences in series. Yeah. Uh-oh. What'd I do? Oh, but I made an even number of mistakes, right? So I made mistakes which cancel. All right, now my mistake is true. This is the problem of much of what's wrong in the world, is that people just make arguments fit what they already believe to be true rather than actually thinking, right? Another example, if we look at 1 plus x squared plus x cubed plus dot, 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 that would be equal to what? So here, identify a is equal to 1, and what's my r equal to in this case? X, yeah. So this says the geometric series that this is equal to a over 1 minus r, provided what? Ooh, exciting. I wonder what it is. Nothing interesting. Actually, something very, very deeply uninteresting. Did not deserve that ringtone. All right. So anyway, provided that the absolute value of x is less than 1. Now, this is a what? I mean, this is like sort of a meta example, right? Because x here can be viewed as a variable. I'm saying this works for any x between -1 and 1 included. Not included, right? If we include 1, what do we get? We get 1 plus 1 plus 1 plus 1, which already proved diverged. That was our first example. If we go to -1, we got 1 minus 1 plus 1 minus 1, and that also diverges. All right. But this actually is a foreshadowing example because this is an example of what's known as a Maclaurin series for the function f of x equals to 1 over 1 minus x. So what we're actually looking at here, guys, is the power series expansion of this function. And the reason that we can't get past x, absolute value of x equals to 1, what's this look like? What's the vertical asymptote? X equal to 1, right? And what's the graph of that look like? At 0, it's at 1, right? And, oh, wait a minute, at 0, it's where? Oh, yeah, it's at 1. So it's got this vertical asymptote, right? And then over here, it does like this. And so what we're finding, or what the geometric series has just calculated for us, is that we can represent this rational function, 1 over 1 minus x, with a power series. This is the power series. All right? And the power series is centered at 0, and it only works from here to here. Do you see why that is? What's it up against? It's up against the vertical asymptote, right? We can't get past it. That's why that's happening. And so this is our ultimate goal, actually, is to understand how we can take functions and replace them with power series. How would you integrate 1 over 1 minus x? Now, that's not a good example because you guys can do it, right? But there's a new way of doing it. You could do this. It's x plus 1/2 x squared plus 1/3 x cubed plus dot, 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 dot. That makes sense. And if you were to differentiate 1 over 1 minus x in this context, you know what it would be equal to? It would be equal to 1 plus 2x plus 3x squared plus dot, 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 dot. In other words, we can integrate and differentiate power series term by term. And that's not a big deal for this example because you already know how to integrate and differentiate this function. But for other more complicated functions, the fact that we can take a function, replace it with a power series, and then do calculus on the power series, well, that's a huge advantage. So that's where we're going. But that's all I wanted to do for today was just to show you the convergence theorem and just introduce the geometric. Next week, we'll be looking at all the convergence tests. So I'm going to end class early today, actually. So, yeah.
So if you were to take the integral of that, would you have to keep going? How many terms would you have to go out?
All the way, all the terms. Yep. Yep.
If r is less than 1, then is it convergent?
If the absolute value of r is less than 1. So between -1 and 1, not included. Anyway, have a good weekend, you guys. I'll see you Monday.